Stereoisomers are compounds with the same molecular formula and the same attachment of atoms, but different spatial configurations. Stereoisomers are divided into two groups, diastereomers and enantiomers. The distinguishing property of these two groups is the reflective symmetry of the molecules. Both diastereomers and enantiomers have different spatial configurations. Diastereomers, however, are not mirror images of one another, while enantiomers are mirror images of one another. Consider these two isomers of 1,2-dichloroethene. Notice that they are cis-trans isomers of one another. The chlorine substituent groups are on either the same or opposite sides of the molecules. Note, however, that there is no way to orient or arrange these two molecules such that they are mirror images. They are not mirror images of one another and are therefore diastereomers. Because they have such unique spatial configurations, diastereomers have differing physical and chemical properties. Conversely, enantiomers are stereoisomers that are mirror images of one another. Each mirrored molecule is called an enantiomorph. Enantiomers must have at least one chiral center, a central atom around which the geometry of the enantiomorphs differs. Because they have such similar spatial configurations, enantiomers have identical physical and chemical properties with one exception. They bend light in opposite directions. Consider these two hypothetical molecules, both with a central carbon bonded to hydroxyl, bromine, chlorine, and amine groups. They cannot be rotated or oriented such that they are the same. They are unique molecules with unique spatial configurations and are therefore stereoisomers. To determine what kind of stereoisomer they are, the symmetry of the molecules must be considered. Note that these two molecules are mirror images of one another and are therefore enantiomers. The differences between these two molecules occur around the central carbon, thus making it the chiral center. Now let's investigate the stereochemistry of a real molecule, lactic acid. Lactic acid has the chemical formula C3H6O3 and exists in two forms, as depicted here. Note that these are unique molecules and cannot be reoriented to be the same and are therefore stereoisomers. Furthermore, they are mirror images of one another and are therefore enantiomers. This symmetry is created by the alternate positioning of carbon 3 and the hydroxyl group around carbon 2. Carbon 2 is therefore the chiral center of lactic acid. Remember, stereoisomers are divided into two categories, diastereomers and enantiomers. Both have identical chemical formulas, attachment of atoms, and different spatial configurations. Diastereomers, however, are not mirror images, while enantiomers are mirror images. Consequently, diastereomers have unique physical and chemical properties, while enantiomers have identical physical and chemical properties with the exception of their optical activity.